Swayam Prabha. Digital India. Educated India.
Welcome everyone to this NPTEL online certification course on techniques of materials characterization. We are in module 10 and we are discussing about X-ray diffraction. So, we just started discussing about the intensity of diffracted beam in the last class. We were mostly discussing about the filter materials, and just we started our discussion on intensity and how the intensity is related to atomic arrangement, what is the importance of calculating this intensity of diffracted beam, and so on and so forth. So, we will be continuing there. We will keep on seeing the Bragg's law from an intensity perspective. We will be then discussing about the scattering by an electron, which is called, there are two types of scattering by an electron. One is the Thomson scattering and another one is Crompton scattering. And then we will see that scattering, X-ray scattering by an atom, how it happens, and we will try to discuss about the atomic scattering factor in this lecture. Okay. So, we have discussed enough about the Bragg's law and how the intensity of diffracted beam on and over the Bragg's law, how it is important and how it is related to atomic arrangement of within a unit cell. So, from that perspective, what we can call or what we can say is that the Bragg's law is a necessary but not sufficient condition for diffraction. Okay. So, if the Bragg's law is satisfied, that is not enough to get a diffracted intensity in the final diffraction pattern. From measurement point of view, satisfying the Bragg's law is definitely a necessary condition, but that is not a sufficient condition for getting a intensity, diffracted intensity. And in that sense, Bragg's law is basically a negative law. So, if the Bragg's law is not satisfied in the first place, so there will not be any diffraction at all. Right. If the lambda value, if the wavelength is not integral multiple of the path difference is not an integral multiple of wavelength of the X-ray beam in the first place, no constructive interference will happen and no diffraction phenomena, no possibility of any diffraction from those atomic plane for that particular direction. That will not be there. That's the first thing. That's why it's a necessary condition. But even if the Bragg's law is satisfied for certain set of atomic planes, still we will not get any diffraction because of the arrangement of atoms in that particular atomic plane. So, that is the point. That is why Bragg's law is just half, satisfying the Bragg's law is just half of the story. The rest half is like the other factors which are basically determining, and we will come to know about that atomic absorption factor, and then most importantly the structure factor, which we just discussed when we were discussing about the X-ray electron diffraction. We just discussed about the structure factor and importance of it. So, we will see here that how the structure factor and the Bragg's law together they determines the entire, or together they tells the entire story of a X-ray diffraction from a crystalline material. Okay, that's where we will be leading. So, at this point we started with the limitations of Bragg's law, and from there we will establish the importance of this atomic arrangement. Okay. So, to establish this relationship between the atomic position and intensity, what we have to consider is that we have to start from very basic. The X-ray scattering from a single electron, how that is happening, then from a single electron, so all the electrons, how they are contributing to the overall electron X-ray scattering of an atom, and finally the same way all the atoms present in an unit cell, how they are contributing to the overall atomic scattering or overall X-ray scattering from an unit cell. So, we will go by these three steps. We will consider the electrons first, then we will consider the atom, and finally we will consider the unit cell, and that is how the entire this derivation, the relationship between diffracted beam intensity and atomic arrangement will derive in that way. Okay. So, first thing, as I said, we will be discussing about the scattering from an electron. First one is the Thomson's effect basically. So, how it happens? So, we know that X-ray beam is basically an electromagnetic wave where this electric field, the strength of this electric field basically varies sinusoidally with time at any given point, with distance at any particular distance, its intensity or this electric field varies with time, and similarly for any given time the electric field also varies with its position. Both of this is there. That's what characterizes basically any electromagnetic wave, and X-ray is just an electromagnetic wave. Now, what happens is when an electron beam interacts with an charged particle like electrons. Okay. So, this the electric field which is there, which is a part of this electromagnetic radiation like X-ray, under the effect of this electric field, now the charged particle electrons will start oscillating about their mean position. Okay. So, you can imagine this to be like a ball is hanging with a string, a ball is hanging, and then you are sort of, a billiard ball is hanging from a string, and you are just sort of applying a force onto it. Another ball, let us say another ball goes and hits it, and then it start oscillating about its mean position. Okay. So, that is what we can imagine, the first kind of an interaction between an electron and which is a charged particle and an electromagnetic wave which is an X-ray photon in this case. Okay. Now, what happens is the electron, when it's set with this oscillation by X-ray photons, the X-ray beam which made the electron or charged particle to oscillate along its mean position, it continuously undergoes an acceleration and deceleration about. So, basically when it, if we just imagine that electron, this is not X-ray, this is not the sinusoidal curve for X-ray, but this is the sinusoidal curve. Let us imagine that for the electron beam, then it is going for an acceleration with certain time, with time it is going through an acceleration, deceleration, and maybe in the other direction again an acceleration, again a deceleration. So, continuous acceleration and deceleration will happen for this charged particle under the effect of this electromagnetic wave. And already we discussed this when we were discussing about X-ray generation, that a charged particles which is undergoing a continuous acceleration and deceleration, particularly deceleration, then it is an excellent source to radiate another electromagnetic wave. So, electromagnetic waves are basically generated by a source which is continuously oscillating, accelerating and deaccelerating. And in charged particle, this is exactly what is happening here, and that is exactly how we generated the continuous spectrum in the first place in the X-ray tube, remember that. So, this is basically this charged particle in this case, which is electron, will in its motion, this oscillatory motion set up by this X-ray photon, it will generate another electromagnetic wave which is another X-ray beam in this case. So, this way we can call it, this basically this entire process is called Thomson's effect, which is discovered by a famous scientist J.J. Thomson, and in this we can call that the incident X-ray beam is being scattered. Basically the electron is just working like a mediator here. X-ray beam comes, hits this electron, it generates an oscillatory motion, and in that rapid acceleration deceleration process it generates another X-ray beam. So, that way basically it scatters the electron incident electron beam, okay, and this is completely, this happens in the first place. Okay. Now, the scattered beam, that scattered X-ray beam which is generated by this Thomson's effect, that will have the same wavelength. So, that is the relationship basically between a charged particle or rather the source which is generated an electromagnetic wave and the wave that itself generated. So, the scattered beam, the wavelength and the frequency of the electromagnetic wave which is generated from this source will have exactly the same wavelength and frequency with which this charge particle or with which this source is basically oscillating. That means the electrons, if I imagine that this electron is there in the middle and this electrons will generate an X-ray, that X-ray, the generated, the produced X-ray will have the same wavelength and frequency as that of this electron beam. Now again this electron, the motion that this oscillatory motion this electron has, this wavelength and frequency is related to the wavelength and frequency of the incident electron, incident X-ray beam. So in that way the scattered X-ray beam will have the same wavelength and frequency as the incident X-ray beam. That means the scattered beam, scattered X-ray beam, the one that is generated from this electron will be coherent with the incident electron beam in terms of wavelength and frequency. And normally they also have a phase relationship between this incident X-ray and the scattered X-ray beam through this electron, okay, and this phase change is usually pi by 2, okay. Between the scattered X-ray beam and the incident X-ray beam, the change in phase is pi by 2, okay. Another important point is that this X-ray, scattered X-ray beam, of course the electron can oscillate in any plane. It's completely a random process. So the scattered X-ray beam also can generate in all possible directions, but the intensity of the scattered X-ray scattered beams will depend. So since this process is completely random, in this case the electron motion is completely random, and this scattered beam which is generated, that also can generate in any random direction, the intensity of the scattered beam will depend on the angle of scattering, the angle that the scattered beam is making with the oscillatory motion or the motion of this electron. So it will depend on that angle, and this equation is basically given by Thomson's. This equation is called Thomson's equation. So the intensity of the beam, the X-ray beam which is scattered by a single electron, which is having a charge of E coulombs and a mass of m, rest mass is m in kg, at a distance r. So this is the intensity. So if you measure the intensity at certain distance from this electron, the electromagnetic wave that is generated due to the oscillatory motion of this electron, if you measure the intensity of it at certain distance r, that is given by this equation, I equals I naught in multiplied with mu naught by 4 square into again multiplied by e raised to the power 4 by m square r square, and this sine square alpha. So alpha is basically here, this is the scattering angle, this is the angle between the scattering direction, the direction of the scattered beam, and the direction of acceleration of the electron, the direction at which the electron is moving and the direction at which the scattered beam is moving. So this is the angle between that. So what you can see, and of course I naught is the intensity of the incident beam, the scattered beam. For the scattered beam basically that is the source of intensity, and mu naught here is the dielectric constant of the medium. Basically this is a constant value. Again m is constant, that is the mass of the electron, and E is the charge of the electron. So overall what happens is this mu naught E m square, all of these are constant. Ultimately we can express this equation in a simpler term, that is I equals I naught into k by r square sine square alpha. So we have only two variables here, that is the distance of like where we are measuring this intensity and this angle, scattering angle, okay. So from this what we can measure the total scattered intensity at certain direction. Now this is something, the derivation I am not going how it is done. The totally scattered intensity, you basically get this electric field vector. You imagine that the X-ray incident X-ray is traveling in this direction, this x direction, OX direction, and at point O you have the electron, and because of that incident X-ray beam, the electrons will start having an electric field which you can then sort of vectorize. You take the components in two different directions, and finally out of that you see this X-ray beam which is coming in another direction. You are measuring the intensity there. So I am not going in details of that, but basically the intensity at any given point P, which is situated at a direction r, at a distance r from this electron charge particle which is generating this this scattered X-ray beam, and this angle which this in this direction, the scattered beam, the direction at which the scattered beam is moving, that scattered beam, the angle it makes with the incident ray. So, this final scattered intensity IP will be I naught k by r square into 1 plus cos square 2 theta by 2. So, this is the final expression for scattered intensity at any given direction, and in that direction the scattered beam intensity, and which in that direction is making an angle 2 theta with the incident beam and at a distance of r. Pretty similar in shape to this earlier Thomson's equation, but here we are measuring it at any arbitrary direction, scattered direction. Here we are measuring at some fixed direction. Okay. Now, couple of things we can realize from this equation. First of all, the intensity of the scattered beam, that is this IP, this one, the entire scattered beam intensity. So, this intensity is basically the scattered beam from one single electron. X-ray beam, which is an electromagnetic wave, hitting a charged particle, which is an electron, generating a scattered beam, scattered X-ray beam. This is the intensity of that overall scattered beam. So, this intensity we can see first of all is very small compared to the intensity of the incident beam. That is simply because that is basically I am taking a ratio of this IP and I naught, which is the intensity of the incident beam, and then I am putting all these values of k, and k is defined, as you know, this is the original equation. K is defined here as this mu naught square by mu naught square into e square by m square. This is what the k value of the constant here. If we put all of these values, then we find that the constant is very small. It is a very small value, and this IP by I naught, this is also a very small, this also has a very small value, meaning that the intensity of the scattered beam is very less as compared to the intensity of the incident X-ray beam. So, that is the first thing. So, most of the intensity of the incident X-ray beam is basically goes into absorption or penetration. Only a very small fraction of it is basically getting scattered by at least one single electrons. That is all. Now, the second thing you can notice is the scattered intensity, this IP, this decreases or this depends inverse, it has an inverse relationship with the distance from the scattered electron, the scattering electron. Okay. So, this distance, so the intensity will also decrease as the inverse square of the distance from the scattering electron. If r is, if we measure the intensity at a further away from this electron which is causing the scattering, then we will be getting much smaller intensity. So, as the distance increases, the intensity goes down. Okay. The third thing we can notice here is from this, that cos theta, this entire term 1 plus cos square theta 2 theta by 2, this term becomes unity if theta equals either in the forward direction theta equals 0 or 2 theta equals basically theta equals 0 or theta equals 180 degree. That means, in the forward direction the scattered beam is strongest in the forward direction, either in this forward direction where we are basically in the same direction where the incident beam is moving. If this is 0 degree, this 2 theta is 0 degree or 180 degree, then this entire term becomes unity, and that is the highest value for IP. Anything in between the 0 and 180, 180 means it is basically retracing, the scattered beam is retracing the incident beam. That is what. Anywhere in between, this will have a fractional value and the intensity will be lower than that in the forward or backward direction. Okay. So, that these three things or these three major conclusions we can draw out of this equation, the total scattered intensity for a X-ray, the incident X-ray or the scattered beam coming out of a interaction between the incident X-ray and the electrons. Okay. This factor, this 1 plus cos square theta 2 theta by 2, this factor is basically called the polarization factor, and this is one of the most very important factor when we will come to this polarization factor when we take the complete intensity or from an unit cell. This again, this polarization factor will come there, and as I just now discussed, this polarization factor is basically one issue which reduces other than the forward or backward direction, it generally causes a reduction in the intensity of the scattered beam from the electrons, and this factor comes in the in this equation simply because the incident X-ray beam is unpolarized. If the incident beam is polarized, we have discussed what is a polarized one. Basically, in a polarized beam, this electric field vector has a particular plane and particular relationship with the magnetic and motion of this X-ray photon. So that's the polarized beam. So I am not going into that. So if it is a polarized beam, then this polarization factor doesn't come into play, and intensity will be pretty higher. The scattered beam intensity is comparatively higher. That is why we want to have a polarized beam. In order to reduce the polarization factor, we want to have a polarized X-ray beam in the first place. So not only monochromatic X-ray beam, we also need to have a plane polarized X-ray beam in order to get the intensity, considerable intensity from the diffracted beam. Okay. So that is the Thomson's effect. Now there is another effect, another way of in which the X-ray beam will be interacting with the the X-ray beam will interact with the electrons. Okay, but for this one we will have to imagine the X-ray to be having the particle. I mean, like we in the quantum mechanics we know that every electromagnetic wave we can imagine them either as a particle or as a wave. So in this case we have to imagine this X-ray beam as a particle, and then we can very easily understand this effect, which is known as the Crompton effect. And this Crompton effect, just like Thomson effect was discovered and proposed by J.J. Thomson, Crompton effect was discovered by A.H. Crompton, another famous scientist, in 1923. So this happens between the X-ray beam or X-ray photons in this case with the loosely bound or free electrons with an atom. If the atom has certain amount of free electrons, then the X-ray beam will interact with them, and the way this interaction happens, we can imagine that it is like a bigger ball, heavier ball is hitting a smaller ball, and so this is the heavier ball, that is the X-ray photon, and this is the electrons, charged particles, which is a smaller ball, and this after the collision, this X-ray will be deviated from its original direction, original path. It will be going in some other direction, but in the process the electron, the smaller ball, will also gain certain amount of kinetic energy. So here it is a static, now it's gained certain amount of kinetic energy from this impacting ball, from this bigger ball, and it will also be moving in another direction. So this, in this process I will get two things. I will get a moving electron, which is generally called the recoil, Crompton recoil electrons, and scattered X-ray beam or this incident beam, which is modified, its energy gets modified due to this impact. So these two things will be generated in a Crompton scattering. Okay. So obviously one thing we can immediately understand, that some amount of energy will be lost in this impact process. So because here this incident ball will have certain amount of energy, now some part of the energy is transferred as a kinetic energy for this recoiling electrons, and only a part of the energy will be retained by this deviated X-ray beam. So obviously the energy of the incident X-ray beam is much higher, or it's higher, at least considerably higher than this scattered electron beam. Consequently, the wavelength of the scattered X-ray beam will be slightly greater than the wavelength of the incident beam. Whatever be the difference between them, the energy difference between them is basically this energy of this electron. So in some sense this process is pretty similar to the fluorescence radiation and photoelectron emission, if you remember. So there also the incident X-ray electron, incident X-ray beam, X-ray photon, whatever it brings, the energy it brings, that energy goes in generating a fluorescence radiation and a photoelectron. Same thing here, in a different way, the incident, whatever energy this incident X-ray photon was bringing, part of it is going as this recoiling electron, kinetic energy of the recoiling electron, and part of it is going as the energy of the scattered beam. So this magnitude of this change in wavelength, and this wavelength of this scattered beam is slightly greater energy, that means energy is slightly lower than this incident X-ray beam. So this magnitude of this change, if we take that as lambda delta, That is basically delta 2 minus delta 1. Delta 2 is the wavelength of this scattered beam minus delta 1 is the wavelength of the incident beam. And from there we can, again I am not going into derivation, we can find out this relationship which is coming out to be around 0.05 around sine square theta, 0.05 sine square theta. So, what is theta here? Basically theta again is the scattering direction, the direction or the angle that the scattered beam is making with the incident beam, just like the Thomson's effect here, just like Thomson's effect where this is the incident beam and this is the scattered beam and 2 theta was the angle between them. Here also in the Crompton scattering, 2 theta is defining the angle between the incident electron beam and the scattered electron beam. So, in that sense theta has pretty much the same meaning between these two things, but only difference is, we will come to that difference of all of this. Only difference is the Thomson's effect is basically an elastic interaction, whereas the Crompton effect is an inelastic interaction, because in the Crompton effect, as you can understand, there is some amount of energy which is lost, whereas in Thomson's effect the energy was not lost. Okay. Now, the increase in energy, as we understand, obviously depends, or the increase in wavelength obviously depends on the scattering angle, only on the scattering angle. Okay. So, this increase in energy or increase in wavelength, rather decrease in energy, increase in wavelength, this varies with direction with this 2 theta angle, and it is this lowest in the, or lowest or 0 in the forward direction, that is 2 theta equals 0 degree in the forward direction. So, if I forward direction means there is no scattering at all basically, or if I imagine that this is the incident photon and this is the electron, if the scattered beam is again even after the interaction it is moving in the same direction, then obviously there is no change in the wavelength. So, it is another way of thinking that there is no change of energy at well, and it will be minimum in the extreme backward direction, that means when 2 theta equals 180 degree, that means this scattered electron or scattered X-ray photon is just tracing back the incident electron, that is what. So, and that value will be obviously 0.05 angstrom, because in that case sin theta will be 1. If it is theta equals 2 theta equals 180 degree, then sin theta will definitely be 1. So, that is the two extremes for this scattered, the change in wavelength of this scattered electron beam. Okay. So, the radiation, of course, this scattered electron beam is called Compton modified radiation, and this electron is called recoiling electrons. And besides, one more important point is that other than change in wavelength, the Crompton modified radiation, this process is pretty much a random process, because it is not certain how much of energy will be transferred to this electron, and how much of energy, it depends on lot of things. So, even if you think that in a bigger ball hitting a smaller ball, it is a complete random process, how much energy will be transferred to this smaller ball and what will be the direction the bigger ball will move. So, the scattered photon, so this process is pretty much again very much random process. So, the way it affects is that the wavelength, definitely in the process of this energy transfer, the wavelength modifies. Other than that, the phase of this Crompton modified radiation, the scattered photon, X-ray photon that generate, that does not have any typical phase relationship with this incident electron, because of this randomness in the process. That means the scattered beam that is generated here is an incoherent to this incident photon. That is another difference between the Thomson's effect and the Crompton effect. Thomson's effect, the scattered beam was completely coherent with the incident X-ray beam, whereas the Crompton modified radiation, this scattered X-ray beam from Crompton radiation, that is having no particular phase relationship or wavelength. Phase relationship means wavelength, frequency, etc. So, wavelength frequency of this one is not at all related to the wavelength of this or frequency of this incident electron. So, in that sense, these are incoherent. This Crompton scattering always generate an incoherent X-ray beam. So, this definitely the Crompton scattering. So, this part of the scattered electron or scattered X-ray beam, this cannot take in a diffraction process in the first place itself, because for taking part in the diffraction, it should have, the scattered beam should have a particular phase relationship with the incident X-ray beam, then only that Bragg's law will be satisfied in the first place. If it doesn't have any phase relationship means lambda has to be, or path difference has to be an integral multiple of lambda, then only constructive interference will happen. If that path difference is not certain, if the lambda of the scattered beam is completely changed with respect to the lambda of the incident beam, then this relationship, this constructive interference, possibility of the constructive interference will also not be satisfied at all. So, this will have, the scattered beam will have a completely random phase relationship with the incident beam, and in the process they will not be able to generate any kind of diffraction phenomena in the first place. So, Crompton scattering is not important to be considered for diffraction purpose. We will be only considering the Thomson's effect, Thomson's beam, because that is what is a coherent, that has exactly the same wavelength as the incident beam. And this difference, obviously now it should be clear that this difference is the way these two effects are happening. One is happening through an elastic interaction mostly, another one is happening by an inelastic interaction mostly. Other than this, of course, there is some the Crompton scattering is also having some importance, because it basically generates the background in the diffraction pattern. It basically darkens the background in the diffraction pattern. We will come to that in a little later, how the Crompton scattering is important for mostly for lighter elements to cause the background or to cause the noise in the signal finally. But one more important difference between Thomson scattering and quantum scattering is that the quantum theory can account for both the coherent and the incoherent scattering. That means both the Thomson and Crompton scattering can be explained using the quantum theory, where we are dealing with the X-ray photons, whereas the wave theory is applicable only to the Thomson scattering. Thomson scattering can be explained both by considering, we have seen how it is, how we can explain the Thomson scattering just by imagining the X-ray to be an electromagnetic wave, and that is interacting with charged particle and generating this another electromagnetic wave. So, from classical wave theory we can explain Thomson's effect, but from classical wave theory we cannot explain the Crompton effect. Crompton effect can only be explained if we imagine the X-rays to be a photon. So, that is another big difference between these two. So, we will be continuing our discussion of scattering by an atom in the next class, and then we will be discussing about atomic scattering factor as well. Thank you. Goodbye.